Alright, so this is number 3 on Module 7, Lesson 1, Assignment 1. And this question looks really simple on the surface, and then when you get into it, it's considerably more difficult than it appears to be on the outside, especially starting off with Part A. Part A is super easy. What is the original momentum of the bullet? Well, momentum equals mass times velocity. I apologize if I don't use the same variables as any other reference table you may be looking at, but between the various classes that I teach, sometimes I don't always pick the right variables for the right class. But anyways, momentum equals mass times velocity, so here you go. So our 0.012 kilogram. It was nice of them to put that in kilograms for us, times 860 meters per second. And when you multiply that out, you don't get exactly 10 kilograms meters per second. You actually get 10.32, but that should be rounded off to, actually I don't like the way they reported the answer. I should have at least 2 significant figures because each of the values used in the calculation have 2 significant figures. So I would report this as 10 with a decimal to indicate that the 0 is significant, kilograms times meters per second. Alright, that was easy enough. Now, that was Part A. Part B, considerably more difficult. So, how long did it take to stop the bullet? Well, obviously when the bullet is entering the sand, it is slowing down. But we only have enough information or we don't have easy information to go from what's given to us to what we're searching for, which is the amount of time it took to stop the bullet. So there are other ways to solve this, but the way that immediately came to mind to me to solve this, since they gave distance, is first off, I felt like I needed to know an acceleration in order to find time. So I set this equation up, Vf squared equals Vi squared plus 2a delta x. Alright, Vf simply enough is 0. Vi was 860. Just for simplicity, and because I'm writing with a mouse, I'm going to leave off some units here. Don't know the acceleration, that's what I'm solving for, and the delta x was 0.24 meters. Okay, now let's move the 860 over. It's negative now. 2 times 0.24 times a, and then we'll divide both sides by 2 times 0.24. And I almost forgot to square the 860, and really I should have done that up here, by the way. And when you solve for a, you get 1,540,833. Meters per second squared. Now, that still is not what we want, because we want to know the time it took to stop the bullet. So we're going to take this information that we just solved for right here, and then we're going to plug it into another kinematic equation. Alright, so our XF we could say is 0.24. Oh, by the way, let's not forget that this acceleration down here would be negative. The XI, we could say our starting point was 0, our initial velocity was 860, the time we don't know and are solving for. The acceleration we do know. Yeah, make sure you put it in as a negative. Alright, so when you go to solve this, there are a couple of ways that you can go about doing this. First off, you need to move the 20.24 over to the other side, so then it'll be negative 0.24. A couple of ways you can handle that. One is you can use the quadratic equation. Two is you can graph it in your graphing calculator, and that is the option that I go with most of the time. When I put that in, I'm using my TI-83 that I keep at home. Some of you may be using a different calculator, which is fine, but anyways, when I graph that, I found it kind of difficult to see where the graph was even at on my TI-83, but what you'll find out is that the 0 is really close to the y-axis, and in fact when I graphed it out I got that the time equals 5.5788 e to the minus 4th, which is essentially the same answer as given, and just to the correct number of significant figures, answer B is correct. So so we'll record that answer as 5.6 e to the minus 4 seconds. Alright, and on to part C. What is the average force that acted on the bullet? This is back to the realm of fairly easy stuff for us to do. So what you need to realize is that the change in momentum equals the impulse. I think we use a J for impulse in AP physics, but we might use an I, and I can't remember, so just know that that's the change in momentum and that's the impulse. So our delta V in this case was from 860 to 0. So technically that would be a negative, which would also make our force times time. It would also make the force in that a negative, which kind of makes sense because the force would be opposing the motion. So you'd say negative 10, because that's the product, that's our momentum from this part up here, equals F times the time that we just solved for, 5.6 e to the minus 4. By the way, when I perform this calculation in my calculator, I will actually go back and use the exact values that were calculated earlier. I would use the 10.4 3 and whatever other decimal places came along with it, as well as with this I'd use the 5.5788 number rather than using the rounded number to give a more precise final answer, and then I would round to the correct number of significant figures at the very end. Alright, so when you carry that calculation out, when I carried the calculation out, I ended up getting this with the non-rounded values, as I just stated, which you might notice does not round to the same thing as the supposed answer key does. And my guess would be because whoever made the answer key probably used the rounded values here. For me as a chemist, I would never do that, but sometimes perhaps physicists do. It's better practice though to use your non-rounded answers in your final calculations and then round to the appropriate number of significant figures at the end. So there you go. I hope you found that helpful, and that's it.